Welcome back to The Explainer. Today we're diving, quite literally, into the ocean's greatest architectural marvels, coral reefs. They cover less than 1% of the entire ocean floor, but incredibly, they actually support a quarter of all known marine life. It's like a giant, bustling underwater metropolis. Today, we're moving past just the pretty pictures. We're going to dig right into the hard biological data to see exactly how these immense ecosystems function, the chemistry behind how they're built, and the highly specific environmental conditions they absolutely need to survive.
Rainforests of the sea. You've probably heard that phrase, right? Well, it's not just some poetic nickname, it's a strict biological analogy. Just like the Amazon is this densely packed engine of biodiversity and super complex food webs on land, coral reefs are the ocean's exact equivalent. They are these bustling hubs of hidden complexity operating with just immense efficiency. But to truly wrap our heads around a macro ecosystem of this scale, we actually have to scale way down and start incredibly small.
Section 1. Meet the coral polyps.
Okay, to really understand the reef, we have to start with the master builders themselves, tiny living organisms called coral polyps. Basically, picture really small, anemone-like animals. But here's the thing, they don't do all this heavy lifting alone. They rely heavily on zooxanthellae. Try saying that 3 times fast. They're microscopic, single-celled algae. And guys, this relationship is a literal masterclass in symbiotic evolution. The coral polyp acts like a physical fortress, giving the algae a protected, nutrient-rich home that's safely anchored to the seafloor. In exchange, the algae act as a sort of solar-powered food factory. Through photosynthesis, these zooxanthellae leak essential sugars, amino acids, and oxygen right back into the polyp's tissues. In fact, they supply up to 90% of the coral's energy needs. Talk about a win-win.
Now, not all corals are created equal. The true architects of the underwater world are the hard or hermatopotropic corals. Supercharged by all that energy from their algae, they have this amazing biological ability to extract dissolved calcium and carbonate ions straight from the seawater. They use this to excrete rigid, rock-like skeletons out of a crystal called aragonite. As generations of polyps die off, new ones just build right on top of that old limestone scaffolding, slowly creating those massive geological structures we know as reefs. On the flip side, we have soft or ahermatopotropic corals. They skip this whole calcium carbonate skeleton process entirely. They look more like swaying underwater forests of trees, fans, and whips. So while they are totally gorgeous and biologically fascinating, they don't leave behind that essential limestone foundation that actually builds a reef. Section 2. Master builders of the sea. So these aragonite architects generally construct 3 massive types of formations. First up, we have fringing reefs. These hug the shorelines directly, extending right out from the landmass into the sea. Second are barrier reefs. Now, these are distinctly separated from the land by vast, deep-water lagoons. And finally, the atoll. These are circular or oval-shaped reefs surrounding a central lagoon, usually way out in the open ocean. And hey, fun fact for you, it was actually Charles Darwin who first accurately theorized how atolls form. He hypothesized that they start out as fringing reefs around a volcanic island. Then over thousands of years, as the island slowly sinks beneath the surface, the coral just keeps growing upward to catch the sunlight, eventually leaving nothing but a growing coral ring behind. Pretty brilliant, right? But here is the catch. These master builders are incredibly finicky. They require a very strict Goldilocks temperature zone, right between 70 and 85 degrees Fahrenheit, or 21 to 29 degrees Celsius. Why so specific? Well, outside this warm little pocket, the enzymatic reactions that drive their calcification process basically slow down to a complete halt. They also demand clear, shallow, and strictly marine water. If they happen to be located near river mouths that are pumping out opaque fresh water, the whole construction site shuts down. That fresh water actually causes lethal osmotic shock to the polyps, and all that suspended sediment blocks the sunlight their symbiotic algae so desperately need to survive. And it's not just about the water chemistry. They also absolutely require a solid, hard-bottom substrate. See, when coral larvae reproduce, they're free-floating. To actually survive, they need a hard surface to permanently anchor themselves to before they can even start secreting their skeleton. Couple that with a steady ocean current that delivers rich, microscopic zooplankton for the polyps to feed on at night, and boom, you have the exact recipe for reef building. But take away any single one of these pillars, the temperature, the salinity, the sunlight, the hard bottom, or the current, and the entire ecosystem fails.
Section 3. Rainforests of the ocean. So what's the real-world payoff here? Their construction provides immense, quantifiable value for us.
Physically speaking, these massive limestone walls act as natural hydrodynamic breakwaters. They absorb up to 97% of incoming wave energy, which dramatically prevents coastal erosion during severe storms. Economically, we're talking billions of dollars generated globally through fisheries and tourism. But honestly, perhaps the most remarkable part is that they are literal underwater pharmacies. The organisms hiding out in the intense biological warfare of these reefs have yielded some incredible life-saving compounds. For instance, chemicals isolated from a Caribbean reef sponge actually led to the development of AZT, which is a breakthrough antiviral drug used to treat HIV, as well as RSC, a vital chemotherapy drug for leukemia. It's just mind-blowing. Section 4. Coral hotspots and habitats. Because they have such strict biological demands, the global distribution of reefs is heavily restricted. We're talking about a very specific warm equatorial band, roughly 30 degrees north to 30 degrees south. They fiercely hug the equator. They have to stay strictly within these boundaries where ocean currents stay warm enough year-round and where solar radiation can penetrate the water deeply enough to keep those symbiotic algae working in absolute overdrive. To actually see this geographic restriction in action, let's look at India's coastal topology. The Andaman and Nicobar Islands in the Bay of Bengal, the Gulf of Mannar down south, and the Gulf of Kutch, they all feature classic fringing reefs clinging right to their shallow coastlines. But journey out into the Arabian Sea to the Lakshadweep Islands, and suddenly you find true spectacular atolls. It's just a perfect real-world showcase of diverse reef architecture thriving precisely within that 30-degree equatorial sweet spot we just talked about. Section 5. Ecosystems under threat. So, it begs the question, how do massive, ancient underwater cities made of solid rock suddenly become vulnerable to rapid, catastrophic collapse? Well, remember that incredibly narrow 70 to 85-degree temperature limit? Spiking ocean temperatures cause the coral to stress out and actually expel their symbiotic algae. It's a fatal starvation process we know as bleaching. Compounding this is ocean acidification. As our oceans absorb excess carbon dioxide from the atmosphere, the water chemistry fundamentally changes, becoming much more acidic. This literally robs the corals of the carbonate ions they need to construct their aragonite skeletons. It's basically dissolving them from the outside in. Add in the intense pressure of overfishing, along with massive influxes of toxic agricultural runoff and sedimentation, and the ecosystem simply begins to suffocate. Honestly, it's death by 1,000 cuts. A reef that's already weakened by temperature stress and bleaching suddenly becomes highly susceptible to rampant coral diseases. The compromised skeletal structure becomes drastically less resilient to the physical battering of tropical storms. Then you add in the localized traumas, careless boat anchors smashing decades of growth, plastic marine debris blocking out essential sunlight, and the rapid invasion of non-native aquatic species that just throw the whole food web out of balance. These master builders simply cannot calcify and rebuild fast enough to survive this compounding onslaught. We've decoded their biology, mapped their precise equatorial locations, and quantified the life-saving medicines hiding right there within their limestone walls. These tiny master builders rely on an impossibly fragile, complex biological balance to construct the largest living structures on Earth. So the real question isn't how these underwater rainforests are built, it's whether we're going to allow them to be unbuilt on our watch. Thanks so much for exploring with us today, and as always, keep seeking out the data.